This video will be to work through using an Ohm's law table on a series circuit. So the equations that we're going to be using to do these calculations are V is equal to IR, and V is for voltage in volts, I is for current in amps, and R is for resistance in ohms. The other equation that we need is P is equal to VI. That P stands for power in watts. Okay. So those are the four kind of variables that we're going to be working with. The only thing that's different as opposed to doing like a basic Ohm's law problem is that we will have now, instead of having just one resistance, we're going to have three resistances, and we have to figure out how that's going to work. So before we get started doing the problem, let's just talk a little bit about what happens to charges in a series circuit. Okay, so according to conventional current, we say that the charges are going to go through the circuit from positive to negative. So when they leave the battery in a series circuit, the charges are going to have to go through each component in the circuit. There's no other way for them to go. And so as they go through that circuit, they're going to lose voltage. So if let's say we start off with 9 volts here. Let's just pretend that our total voltage is 9 volts. Okay? And let's say that each of these resistors is 3 ohms. They won't always be equal, but they could be. Okay? So if they have 3 ohms, then that means that each one is going to use up a third of the energy. Because remember, voltage is just energy per charged particle. So as the charge goes through here, it's going to have 9 volts. It's going to have to use some energy to get through this resistor. So let's say it loses, a third of 9 would be 3. So after it leaves that resistor, it would have 6 volts. Okay, that's where we say, okay, let's hook up a voltmeter across this resistor. That voltmeter would be able to tell us the difference in potential energy before and after the resistor. So that would say that we dropped 3 volts. Okay. Again, it would drop 3 volts after it goes through the second resistor. As long as the resistances are the same, we can assume there would be 1/3 of the voltage the entire way through. So here it would still be 6 volts. After that, it would be 3 volts. Okay? Then it would have to use another 3 volts when it goes through the last resistor. So it would have 3 volts here, and then it would have 0 volts when it gets back to the battery. That's why it's called a voltage drop. It kind of starts out at 9 volts, then it drops to 6 volts, then it drops to 3 volts, and then it gets to 0 volts, all because it had to spend some energy to get through the resistors. So, having done that one, those numbers were fairly pretty. So let's go ahead and say that we are going to do another circuit for the math. So I'm going to change colors here. And I'm going to say that our new circuit is going to look like this. This time, let's say we have 24 volts in our battery, and our resistors are 3 ohms for 1, 6 ohms for 2, and 9 ohms for 3. So we have our chart set up here, and basically this chart is just using Ohm's law to help you keep track of your information. So we know that V is equal to I times R, and power we'll get to in a little bit, so pretend there's a little invisible line there. Okay, so the first step to using this chart is to plug in all of your given values. Well, we said that we had 24 total volts. Okay, so we're going to put that in total, and then each resistor has its own resistance. So we're going to write those down. 3, 6, and 9. Okay. So back up to talking about, or also including those circuit properties. We said that in class, we said that current was constant in a series circuit. That is because if they have to go through all of these circuit elements, then only so many can go through at a time. And so when it's limited at one, it's limited at all of them. So current is constant in a series. That means if I were to take an ammeter reading here, it would match an ammeter reading here, an ammeter reading here, and an ammeter reading here. The current is the same at all of the places in that circuit. It doesn't mean current can never change, it just means it's the same at all places in a series circuit. So we also said that resistance is additive. Okay, when we built our circuits, we saw that if we just had one light bulb, it was bright. If we had 2 light bulbs, it wasn't as bright. And if it had 3 light bulbs, it was dim and sometimes we couldn't even see it. That's because as we add resistors, the total resistance of the circuit goes up. So when we say resistance is additive, if we wanted to find the total or equivalent resistance of this circuit, we could just do 3 plus 6 plus 9 equals our total answer, which is going to be 18 ohms in this case. So that's what we mean when we say resistance is additive. Now, using our Ohm's law formula, V is equal to IR, we have total voltage, we have total resistance, so we can calculate total current. So VT is equal to IT times RT, and the T's just mean total, you don't have to write those. So 24 is equal to I times 18. We're going to have to divide both sides by 18, and in this case we are going to get 1.333333. So 1.33 amps is equal to our total current. Okay, so I'm going to put that here in this total current box, and because it's a series circuit, okay, because it's a series circuit, that means if the current is 1.33 at the battery, it's 1.33 at resistor 3, 1.33 at resistor 2, and 1.33 at resistor 1. So now it becomes very simple to calculate how much voltage is used to go through each resistor, because we know that V is equal to I times R. So 1.33 times 3 would give us 3.99. 1.33 times 6 gives us 7.98, and 1.33 times 9 gives us 11.97. Okay, and those numbers look kind of funky. Sometimes the math works out really pretty, and sometimes the math works out where you have a lot of decimals. Just because you get decimals like that, it does not mean that you did something wrong. Okay, so a way that we can check ourselves, because those numbers do look kind of funny, is we also know that in a series circuit, voltage is additive. That means we can take the voltage at resistor 1 plus the voltage at resistor 2 plus the voltage at resistor 3, and it should equal the total voltage. So if I plug in 3.99 plus 7.98 plus 11.97, I get 23.94, which is very close to 24, so we're okay. You're in trouble if instead of getting 24 you get 48 or you get 3, but we're close enough here. Okay? The power row really or column really doesn't have to be included, but it's nice to have, especially if your problem asks you about one or more resistors, how much power they have, like what's the power of this light bulb. Power, remember, according to our formula, is voltage times current. Okay, so if we do 3.99 times 1.33, that gives us 5.31 watts for R1. 7.98 times 1.33 gives us 10.61 watts for light bulb 2, resistor 2. And then 11.97 times 1.33 gives us 15.92 watts. So our total would be our total voltage times our total current. So 24 times 1.33, and that would be 31.92 watts. And if we add those up, we should get something very close to that. So this bulb, R3, is the brightest. So we would expect this bulb, or I'm sorry, it has the biggest power, which means we would expect it to be the brightest. R2 has the middle, and then R1 has the least. So we would expect that to be the most dim. And that has to do with R3 has a higher resistance, so it had to lose more energy to get through. I hope this has been helpful. You are welcome to this sheet to change like I just did. I just made up the resistances and the voltages, and you can do that and solve your own problems, and as long as these add to this, you're golden. If you have any questions, please feel free to ask. Otherwise, I hope this has been helpful.